All right. Thank you very much, and good morning. And thanks indeed for the introduction, and thanks for the invitation. And it's I'm very pleased to give this talk here, to take part in this conference. And indeed, I regret that I couldn't make it to Bonn as of now, and I do hope that there would be occasion in the near future, maybe towards the end of the trimester, to meet at least some of you in person. So today I would like to tell you something about an ongoing project, an investigation that I've been conducting for quite some time now. And as you can read on the slide, this is joint effort with Giacomo, who is also here in this trimester, and with our common postdoc supervisor, Filip Rindler, here at Warwick. In a nutshell, somehow the overarching goal of this project is to identify, to explore yet another bridge between two different areas, though very closely related. And that is, on the one hand, calculus of variation, material sciences; on the other side, instead, PDEs, and most notably the transport equation, and somehow GMT. There's, as you will see, there is some rectifiability issues also lurking in the background, and I hope that you can find these interesting. So before really diving into the matter, let me just briefly outline what I would like to tell you today. So I'll start by providing you with some motivations behind our study, and with a very quick, mostly notational summary of the theory of Euclidean currents. And building on the notations that I will have introduced, I'll be able to write down a PDE, an equation that I want to consider on the space of currents, which is this Lie transport equation. And I'll finally present you our findings concerning this geometric Rademacher type theorem on currents that we have found along the way. And if time allows, I'll present you a few glimpses from its proof. All right, so without further ado, let me properly start, and as anticipated, let me give you somehow some motivations behind our work. So our study, in a sense, really pivots around the understanding of the mechanisms which lie at the very basis of plastic deformations of materials, okay, crystalline materials. So essentially, it's a question that stems really from applied math, if you want. And one of the fundamental concepts in this regards is given by dislocations. So I don't want to enter into the details of what a dislocation is, also because I'm by no means an expert in this, but let me tell you my basic understanding, or at least let me present you a way in which you can understand a dislocation. So dislocations could be thought of as defects, as topological defects inside the lattice of a crystalline material. And indeed, if you want a sort of concrete way to understand dislocation, is if you give yourself a loop, a circuit in the lattice of a crystalline material, and you count somehow the atoms or the atomic bonds that such a loop encompasses, and you kind of compare this with some reference configuration, then every time that you encounter a mismatch, every time that you find a sort of mistake in this computation, then more or less by definition you have a dislocation. Now, of course, people have been trying to cast this into mathematics terms, into rigorously mathematics terms, and have been trying to formalize this from the mathematics viewpoint for quite some time with increasing level of sophistications. And nowadays, one of the ways in which you can model dislocations is via integral one currents in R3. And now, since dislocations inside the material move according to the forces that are exerted on the material, it's rather natural to look for evolutionary models on dislocations, that is, evolutionary models on currents. And among the evolutionary problems that we could consider, we've chosen, and we would like to investigate the transport of dislocations, that is the transport of currents, right? And let me somehow highlight here that So very broadly speaking, these locations are one-dimensional objects that are moving inside a three-dimensional object. So somehow our problem is truly codimension 2 problem. And you'll see that this plays somehow a role later on in the talk. So let me, as I mentioned before, let me quickly brush up the theory of currents. So I'm sure that most of you, perhaps all of you, are very familiar with this, but let me set somehow the notation for my talk. So a K-current is defined as a linear and continuous functional on the space of smooth, compactly supported K-forms. And well, in a sense, K-currents can be thought of as vector-valued or multi-vector valued analog of distributions, or in another way, if you want, as generalized surfaces. To some extent, this is the same analogy that we have when thinking to distributions as generalized functions. But say the analogy, so the analogy as the understanding of a K-current in terms of a generalized surface allows me to introduce these two notions that play a crucial role in the theory of currents, that are the boundary operator, that is defined here on the slide, and it's somehow reminiscent of the boundary of the surface in case of a smooth, of a current induced by a smooth surface. And you can check that this definition, which is given out of duality, right? It's just the dual, the dual operator, the adjoint operator, if you want, with respect to the RAM differential. You can check that this is a well-posed definition. So if you start from a K current, this defines an object which acts linearly and continuously on K-1 forms. And instead, it's a quantity that generalizes the notion of area of a surface is what we call mass of a current, right? And it's defined here on the slide. And as far as this talk is concerned, every current will basically be of finite mass. And when we restrict to currents with finite mass, the analogy and say the understanding of K currents as multi-vector value distributions is actually effective and can be rigorously proved. So to be precise, to be more precise, let me recall that in the case K equal to 0, so 0 currents with finite mass can really be identified with scalar measures with finite total variation. And more in general, for K currents, when K is greater than 0, every K current with finite mass can be written in this form. So as a measure, taking values in the space of K vectors, right? And so actually, not only will I restrict to the attention to currents of finite mass, but actually we will consider special subclasses of currents in this talk. And among the subclasses, it's worth mentioning the normal currents, which are the currents for which both the mass of T, the mass of the current, and the mass of its boundary are finite. And most notably for this talk, I'll consider integer rectifiable currents, IR currents. And those are currents such that their representation as a vector, multi-vector valued measure as somehow a special form. And it takes precisely the form that I've written on the slide. So it's the Hausdorff, the K-dimensional Hausdorff measure restricted to some rectifiable or K-countably rectifiable set E. The multi-vector is given by the wedge product of the vectors that are an orthonormal basis of the tangent space, the approximate tangent space of E. And if we want, we can consider also and multiply everything by an L1 integer valued density. So here's a picture that I like you to keep in mind for the duration of this talk. Somehow, I mean, it's a picture that should simplify, should clarify a way in which we can think to one currents, integer rectifiable boundaryless one currents. And you can think to them as just as a collection of Lipschitz loops, right? So every time that I will be saying, consider an integer rectifiable one current with zero boundary in RD, there is no loss of generality in understanding it as just a superposition of Lipschitz, countably many Lipschitz loops, which are actually injective up to the initial and final points. This is actually a theorem that you can prove it, and it's say the general structure of this type of currents. I need now one more operator on the set of space of currents, which it won't come as a surprise. It's defined once again in terms of duality with respect to the smooth forms, the differential forms. And this operator is the Lie derivative. So what is the Lie derivative of a current? Well, I have to start with a vector field. So suppose that I'm given a vector field B. I define the Lie derivative of a current T with respect to the vector field B as simply the action of T on up to a sign onto the Lie derivative of the form omega, right? Of the test form omega. And the Lie derivative of a K form with respect to a vector field is classically defined, as I have recalled here at the beginning of the slide. It's if you want it measures the evolution of the form along the flow of the vector field, right? And for those of you who are more acquainted and know more about the theory of currents, it can actually be, I mean, it's possible to derive a fairly explicit formula for the Lie derivative of a current, explicit in terms of the current itself, the vector field B, and somehow the boundary and the wedge operator. And it's precisely this formula that I've written in this blue box, and it can be obtained very easily dualizing the so-called Cartan's magic formula, which is I guess very well known, and it relates the Lie derivative of a form with the differential, the RAM differential, and the contraction with the vector field. But in any case, with this definition at hand, I can now tell you, I can now write down the PDE that we would like to consider on the space of currents. And we will be working with the transport equation, this Lie transport equation on the space of currents. So I am given now, I suppose that I'm given a vector field B and an initial datum, so a current T bar. And I'm looking for families of currents, T indexed by time, with the property that the time derivative of this family of the current at time t equals, plus the Lie derivative of the current equals identically vanishes in 0,1 times RT. So we have not been able to find in the literature that we have looked through, we've not been able to find a thorough analysis of this PDE. And I'm just mentioning here a few instances that we've been able to spot. So such an equation has been considered by François Bouchou in some unpublished slides, but not really this equation in terms of current, but rather it's somehow the dual formulation with K forms. And this equation also features in Kamschulte's PhD thesis of the 2017, where he considers this equation associated with C1 smooth vector fields, and in connection with some problems with gradient flows on the space of currents. And although it's not really this equation, but it also appears, or it's related to some work by Jan Brenier on magnetohydrodynamics equation around 10 years ago. But before going on, let me discuss with you somehow two particular cases, and let us check what we can say into extreme cases. So I invite you for a moment to set K equal to 0. So to consider this equation on the space of zero currents. Well, as I told you before, zero currents with finite mass are measures. So TT is actually something that we can write as mu t, it's a path of measures. And its very easy computation shows that the Lie derivative operator in this case reduces to the divergence of the product B times mu. And what we obtain in this case is what is normally traditionally called the continuity equation for the measures mu t. On the other end of the spectrum, so when we are in the top dimensional case, when k is equal to d, it can be proved that currents are actually, sort of sign volumes. So you can find a scalar function u for which such a representation holds true in this top dimensional case. And once you realize that in this case, the Lie derivative reduces to the directional derivative in the direction of the vector field, the PDE that we are considering reduces to the transport equation. And so somehow we have identified a sort of spectrum from these two extreme cases, from the k equal to 0 and the k equal to d. And let me present you the first, known Well-Posner's result for this equation, but I think it's worth mentioning it. So we do have a Well-Posner's result for this PDE as soon as the vector field is Lipschitz continuous. And this is also related, if you want, to the geometric meaning of the PDE itself, because let me first state and then comment the statement. So whenever you have a Lipschitz continuous vector field, then you know that there exists by classical theorems a unique flow, which is Lipschitz itself. And then you can prove quite easily that there exists a unique solution to the PDE. And you can prove that this formula, this representation, holds true. So the solution is the push forward of the initial datum along the flow of P. And so again, the push forward is classically defined. It's an operation that we can perform on currents, and it's defined here on the slide, once again by duality with respect to the pullback of the form. But behind this formula, there is somehow the geometric meaning of the PDE, because what I am really doing is I am transporting my initial datum, my initial current, under the flow of the vector field. Okay, and such a formula, such a Well-Posner result is totally consistent with what happens in the two extreme cases, which are perhaps more widely known. And namely, when k is equal to 0, so when we have the continuity equation, it can be shown very easily that the push forward of zero current is the same thing as the push forward of a measure. And so we obtain this formula, which is the standard formula for the solutions to the continuity equation, somehow preserving the total mass of the measure. While instead, in the top dimensional case, the push forward with respect to a map reduces to the precomposition with the inverse of the map, and you obtain this formula, which is the formula that you obtain, for instance, if you apply the method of characteristics to the transport equation. So there is this total consistency with the two extreme cases, but nonetheless, I would like to mention that it seems rather difficult to extend this Well-Posner's result to rough vector fields, so to vector fields which are less than Lipschitz. Now, there's quite a vast literature on the transport equation and also the continuity equation associated with rough vector fields, and this is somehow the area where I originally come from. But it seems rather difficult to pursue this direction here. And there are essentially two reasons behind this. On the one side, there is complete lack of a priori estimates for this equation in the intermediate cases, so when k is not 0, neither 0 nor d. And on the other side, it might be also due to the singularities of the irregular Lagrangian flow, which is the by now classical tool to study the transport and the continuity equation in the non-smooth regime. However, such a notion of flow is very far from being Lipschitz in general, and so it's not clear how to conduct this study and to define, for instance, the push forward with respect to a map which is not Lipschitz. So nonetheless, there are a couple of questions that we can still address related to the PDE, to this transport, lead transport PDE on currents. And I'd like to tell you something about a question that we asked ourselves and we have solved. And this stems from the from this very elementary observation. So suppose now that I am given a vector field, which is, say, just a bounded vector field, and suppose that I am given a solution. So I'm given a family of integer rectifiable k-currents which are solving the PDE. Okay, and suppose in addition, at least for the time being, that they are boundaryless. And what you can show very easily is that you somehow gain a tad of regularity in time. That is, the map that goes from the reals to the space of integer rectifiable currents is Lipschitz. So T2 maps to TT is a Lipschitz continuous map. Now, of course, I'm saying Lipschitz, so I have to define a distance on the space of currents, right, in order to make this, to give a meaning to this notion. And of course, the metric that I am equipping the space of currents with is the flat distance, well, to be more precise, in this case, it's the homogeneous flat distance. And I have recalled the definition here on the slide. It's a very standard distance. It's a very standard metric to work with when dealing with currents. It's, if you want, a generalization of the Wasserstein distance between two measures. And indeed, you can check that it's this distance, this flat distance, metrizes actually the weak convergence of currents on bounded sets. And if you want an idea, I mean, the heuristic behind its definition is that if you suppose you're given T1 and T2 that are two loops, really two currents associated with two loops, then the homogeneous flat distance is the area shaded in blue, so somehow the area between the two loops. So this observation, therefore, is saying whenever I have a solution to the PDE, and say it's boundaryless, then this map is Lipschitz. What we are asking now is, does the converse hold? So, namely, suppose now, just reverse the role. So suppose that we are given now a map from the reals to the space of currents. Suppose that maps to boundaryless currents. And suppose that such a map is Lipschitz with respect to the homogeneous flat distance. Can we find a velocity field? Can we find a vector field B, which is sort of driving their evolutions, which is, so can we find a velocity field B, which is solving this PDE? It's rather clear that if such a vector field existed, it could be thought of as a sort of geometric derivative of the Lipschitz map T to TT, right? So, of course, this is not a derivative, this is not a differential with respect to the linear structure of currents. It's a sort of derivative which carries a more geometric meaning, indeed. And with I mean, considering the picture that I asked you to keep in mind, so if you suppose that you are given a family of Lipschitz loops that are wandering around in R3, and you happen to know only this Lipschitz regularity with respect to T, so you know this, you have this Lipschitz regularity with respect to the flat distance, then I'm asking, can we find a vector field, can we find a velocity field which is advecting these loops, which is moving these loops around? And again, let me start considering one of the two extreme cases, and the case k equal to 0, so when T is a measure, I would say that the answer is yes, and it's sort of textbook classic by now, because it's one of the ways in which the continuity equation can be introduced, actually, and you can check the details of the proof if you want in the standard reference by Ambrosio, Gigli, and Savaret. But here is our main contribution, because we have been able to extend such an answer to, I would say, two particular cases, which are the codimension 1 and codimension 2 cases. So the answer to this question that was posing is still affirmative whenever the TT are, so the currents are integer rectifiable, and K lies in this set. And let me somehow emphasize that whenever the space dimension is 3, I mean, every meaningful case is really being covered. So we have this Rademacher type theorem for currents, for integer rectifiable currents, and I'd like to spend the remaining few minutes of my talk just to present you the ideas behind the proof, behind our proof. The proof could be split somehow into two parts, and here is the first. I'm slightly changing the point of view here, and the first part of the proof, what we do is we study a possible generalization of the level set approach tailored for currents. So the level set approach is a commonly used tool to describe evolution of surfaces, like for instance in the mean curvature flow. So we are trying to adapt this somehow to this to the case of currents, and let me tell you somehow a bit more precisely what we want to do. So indeed, suppose for a moment, I'm changing a bit the setting now, but suppose for a moment that I am given a pipe, so a cylinder in the space-time, or more precisely, suppose that I am given in the space-time R cross RD, I'm given an integer rectifiable current, 1 plus K current, S, which is a space-time current, right? So I have this cylinder, this pipe in the space-time, and what I can do is, relying on the slicing theorem for currents, for integer rectifiable currents, I can slice this current, this K plus 1 map, this K plus 1 current with respect to the projection onto the time of the Lipschitz projection onto the time axis. And what I obtain via this slicing theorem, modulo some projection, can be identified with a K current, an integer rectifiable K current in RD. Okay. And well, taking advantage of the space-time structure, so of the fact that I have this pipe, which I was assuming to be rectifiable, I can define a vector field B, which is advecting the slices ST. All right. So if you want, this recipe is telling me that whenever I have this space-time structure, so whenever I have this pipe, I can always slice it with respect to the time variable, and I can find in this case a vector field which is advecting which is driving the evolution of the slices. Okay, and this is the content of this lemma, if you want. So whenever I have this space-time structure, we can indeed find a geometric derivative of the map given by the slices of this pipe, right? And I guess that now you see that I have been somehow shifting the problem to a rectifiability question, because now the problem becomes the following. Suppose that I start from my collection of loops that are wandering around in a space. What I want to do is I want to find a way to pile them up, and in such a way that this pipe that I obtained, this cylinder, is a K plus 1 rectifiable current in R times RD, right? And so here is the question that, as you see, is really a rectifiability flavor inside. And it's, so whenever I have this family, this map, which is Lipschitz, and with respect to the flat distance, can we find a way to pile currents up in such a way that the resulting current is k+1 integer rectifiable. And again, the answer in the case k = 0 was known, and it's contained in this very influential and deep paper of the 2000 by Ambrosio and Kirchheim on the structure of metric currents. But inside there is this very deep lemma, this very deep rectifiability result. And we have extended this to the codimension 1 and codimension 2 cases. And let me just mention that this question readily translates into somehow an abstract question, which is concerned with the very definition of flat distance of the flat norm. And what we ultimately need is somehow the equivalence between the normal flat distance, the normal flat norm, if you want, and the integral flat integral flat distance. And in any case, we are able to establish such an equivalence in these cases, relying on somehow classical works of the 80s on the structure of currents by Arden Pitts and by Zworsky. And so you see, combining these two parts of the proof, so piling the loops, piling the currents, and giving them a rectifiable spacetime structure, we are then able to find this vector field, this velocity field B, which is which is driving the revolution, and indeed it acts as a sort of geometric derivative. And well, I think that's everything that I wanted to tell you today, and I thank you all very much for your kind attention.